Well, I will begin. I am going to try to make it my habit to end physics early so I can start this class on time. Yeah.
Did we do compound a few times just to make up a couple times?
No. Not today. All right, so I'll begin with a word of prayer. Dearly Father, we thank you for this day, and thank you for the students. Just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So we are now all the way to chapter 2. And today I'm going to talk to you guys about vector spaces. Now, the concept of vector space, a relatively modern concept. I think the definition probably was first stated, I don't know, how many years ago now? 120, 130 years ago maybe? But of course people have been working with vector spaces before then. Essentially, like in a nutshell, a vector space is simply a set where you can add things together and you can multiply by scalars from a field. Right? That's what a vector space is. So, but we'll be more precise than that. I'm going to state for you the definition in all of its glory. So it'll take me a minute to write this out. Here it goes. Definition. A vector space V over a field F is a non-empty set V together with a vector addition plus, which is a mapping from V cross V to V again, it's a function, and scalar multiplication, which we sometimes denote by a dot. Well, we use a dot for the sake of this definition, but generally speaking, we just use juxtaposition for the scalar multiplication, and that takes in a pair, a field and a vector, and it outputs a vector again. All right. And so that's called scalar multiplication, and that's called vector addition, and they have to satisfy the following 10 axioms. Now, this list of axioms is by no means logically minimal. Like, it could be replaced with a smaller set of axioms, and some of these axioms could be derived as theorems. I'm trying to find a better marker. Axiom 1. There we go. Axiom 2. Axiom 3. Axiom 4. Axiom 5. And if you don't mind, I'm going to write these axioms in a slightly slovenly way, in the sense I'm not putting the qualifiers, all right? So x plus y is equal to y plus x. X plus y plus z makes sense. In other words, I have parentheses here and there. So addition is commutative, addition is associative. I'll put some qualifiers here. There exists 0 in V such that x plus 0 is equal to x is equal to 0 plus x for all x in V. Axiom 4, for each x in V, there exists minus x in V such that x plus minus x is equal to the 0 vector. Axiom 5. Okay. Axiom 5, 1 times x is equal to, well, x for all x in V. And that is, this 1 is 1 in the scalars, all right? Axiom 6 Axiom 6 states that AB scalar multiplied by x is equal to A scalar multiplied by B scalar multiplied by x. Right. Axiom 7 is that A scalar multiplied by the vector sum of x plus y is A scalar multiplied x plus A scalar multiplied by y. Axiom 8 is that the scalar sum of A plus B scalar multiplied by x is the scalar multiple of A by x plus the scalar multiple of B by x. Axioms 9 and 10 I kind of already stated, but I'll state them again here, is that x plus y is single element in V, and likewise c times x is single element in V. All right. Now the qualifiers I haven't written are basically for all x and y, for all x, y, and z, you know, okay? For all a and b, or for all a, b, and x. The last two aren't really needed in some regard, because once I write this right here, this notation means that plus and scalar multiplication are functions, right? This notation implicits a function, that plus and scalar dot is a function, and as such it's single valued. But just to be extra super clear, vector addition has to be a single thing. You can't do vector addition of two vectors and get two different things two different times, you know? Any questions? What don't you see here?
Multiplication is commutative.
Yeah, multiplication is commutative. It's not even defined. Like the multiplication of vectors is not defined. We define scalar multiplication, but not. And the scalar multiplication is assumed to be commutative because it's from a field. So there is that backdrop. That's a good question. So a field, remember we talked about that before. It's a commutative ring with identity such that every non-zero element has a multiplicative inverse. So, and we have further notation. Further notation is we write V over F to emphasize that V is a vector space with field of scalars F. All right? This matters because for a given point set, there's more than one possible vector space structure. All right? So let's look at some examples. So of course the quintessential example, I guess I'll just number these examples. Number one, V equals to Rn over R, right? So the way that works, of course, is x plus y, the ith component of it is x sub I plus y sub I, and cx sub I is equal to cx sub I, right? Those are our usual definitions for vector addition and scalar multiplication, and those indeed satisfy these axioms, right? So just to talk about the axioms a little bit more, axioms 1 through 4 essentially make vector addition give the vector space the structure of what's called an abelian group. An abelian group is simply a set that has an operation, and that operation is associative and commutative. And that's what vector addition is. It's an associative commutative operation where every element has an inverse. See, every vector has an additive inverse, even 0, right? So the first 4 axioms make the vector space an abelian group under addition. Then the next 4 axioms really concern the interaction of scalar multiplication with vector addition, right? So that's kind of something new. It's kind of sort of like the idea of a ring and its multiplication, but it's kind of different. Anyway, enough about that. So this is a vector space, all right? Now, we could just as well do Like, we could talk about Rn over the rationals. See, then this right here was for x, y, in the real in Rn, and for C and R, right? X in the rationals, again, we would define vector addition the same way, but when we define scalar multiplication, this would be for x in the Rn and C in the rational numbers. See, if I take a rational number multiplication of a real vector, it's still a real vector. It still checks all the axioms. But that's a different vector space. If you're only allowed to multiply by rational scalars, it's a different vector space than if you're allowed to multiply by real scalars. So of course, number 2, you could take V equal to m by n matrices, right? With the usual addition and scalar multiplication forms a vector space. The sum of two matrices is a matrix of the same size. And scalar multiplication of matrices satisfies all those axioms. So this is a vector space. Again, you could also talk about the related but different vector space of Rm by n over the rationals, where you define addition of matrices the same way, but you only allow scalar multiplication by rational numbers. That would still be a vector space, but a different one. Right? Yeah.
Does the field you use have to be a subset of the one-dimensional version of the vector space? So like if you have real m by n of the complex, for instance, that would make sense.
We'll get to that. You could, well, maybe that's the same thing. I think in some sense what you're saying, what you're asking, the answer is yes. It has to be kind of a subset of the things you're working with. Otherwise you can't extract it or put it back in with the scalar multiplication, right? Like if there's no, here. So for a non-example, what we couldn't do is try to look at like R2 as a complex vector space. Like that wouldn't work. When we tried to make the definition A plus IB, times the vector xy, if we tried to do the natural thing, which would be this, well, that doesn't work, right? Because this is in C, right? And this is a complex number. It's not, that definition of scalar multiplication by complex numbers would not be a function into R2. We'd start with an R2 vector, and what would come out would be a C2 vector. That's not scalar multiplication. Now, a much harder question to answer is it possible to make R2 a complex vector space with respect to some notion of complex scalar multiplication? And the answer there is yes, but not probably not in this way. We'll get to that actually in just a second here. 3, we could let V equal to, let me just get straight to the point here. We can do m by n complex matrices. That is most naturally, this is a vector. Here we can take F equals to C. That's the natural thing to do. We talk about m by n complex matrices as a complex vector space. We take the complex scalars. But you're right, we could take that and we could restrict it. This wasn't really your question, but we could restrict that. We could instead use just real scalars, or we could even just use rational scalars, and that would give us the related but different. It's related because they're the same point sets. It's not the same vector spaces because it has different scalar multiplication, All right. Now, 4 though, if we look at, so here's the thing, what I was talking about a second ago, Sam, is like if we take V equals to C, well then C is R2. And so there, since C is R2, in that sense I can make R2 a complex vector space. So actually any even dimensional real vector space I could envision as a complex vector space by playing this game. Essentially I can take R2n and I can look at it as Cn, and I can make this a complex vector space if I think of it as that. But anyway, let me get back to the easier examples. You're tempting me. All right, so start with matrices over the reals, complex or rational numbers. These are all vector spaces. What else is there? Let's see here. So we can sort of extrapolate these examples. So 5, more generally, if you just take V as, say, m by n matrices over a field, right? Where we define the matrix addition and scalar multiplication as usual. So I could have just written that as my example 1 and said take f equals to c, f equals to r, f equals to q, right? But I thought by writing these out as 5 different things it would help you guys, right? All right, so there's more. This next example is really quite different. Let S be a set. Then we can talk about the functions from S into, well, let's see here, what I start with. I'll tell you, well, let me be, yeah, fine, I'll start with real valued. So we've got f from S to R. Thank you. I was about to do that. So this is a vector space. The set of real valued functions from a set. Which set? Whatever you want. I mean, I'd like to be non-empty, you know, just to not be weird, but this is called function space. How do you think we should add 2 vectors in this space? If I have f and I have g, and let me call this vector space v, in v, then f plus g, how should we define it? How did you add functions in pre-calculus? Oh, composites. That's later. We're not there yet.
Okay.
No, easier than that.
Added their elements together?
Add their elements. What's the rule? We say it's defined point-wise, right? So you say f plus g of x is equal to f of x plus g of x for all x in S. You just define addition of functions point-wise. Remember, if you define the rule for all elements of the domain, you've defined a new function, namely f plus g. That makes sense for real domains. It still makes sense for abstract domains. I mean, S could be a set of chickens or something, right? How about if C is a real number, then how should we define CF? The new function, the scalar multiple of f by C, how's that defined? Yeah?
C times f of x.
C times f of x, you got it. That wasn't bad, was it? So that's for all x in S. So that defines this, you know, this defines f plus g is going to be in V, and of course CF is also an element of V. And you can run through it. This addition, this scalar multiplication will satisfy all of those axioms. What's 0? What's the 0 function? If I use z, Z for 0. How do you define it? Z of x equals to what? 0 for all x in S, right? Customarily, we just write Z is equal to 0. As I mentioned in the notes, 0 is a terribly degenerate thing. It has so many different meanings, right? Is it the 0 function? Is it the 0 matrix? Is it the 0 2 by 2 matrix, 3 by 3 matrix, 3 by 2 matrix, 4 by 4 matrix? I mean, there's so many different zeros, but we use 0 for all of them. And you guys aren't usually bothered by it. I shouldn't have pointed this out. You're going to demand a notation for me to distinguish my zeros. I'm just kidding, you won't do that. Can we take this example and extract from it infinitely more examples? Elliot looks excited. Let's see here. So 7, what if we did this? If we let W be vector space over a field F, and then let V equal the function space from a set S into W. This is a vector space for the same reason as 6. Because if I take F and G in this, newfangled function space here, then I can look at F. First of all, I can define F plus G of little w equal to F of W plus G of W for all W and W. And I can like C times F acting on W equal to CF of W for all W and W, and C in the scalar field. And why would this be defined? If W is a vector space over F, what does it come with? It comes with vector addition, and it comes with scalar multiplication, right? So the fact that W is a vector space over F means I can write this, and I can write that. See, vector addition, this is the F of W and G of W are by definition vectors in W. So I can add them, and I can scalar multiply them. So I'm not just limited to real valued functions. Real valued functions is just to make it seem more familiar to you guys. We can just as well think of complex valued functions. Goodness, we could think about 2 by 2 matrix valued functions, right? The options here are limitless. There are so many vector spaces which are not just column vectors. I hope this starts to make that clear, right? The other examples that we often cite are polynomial examples. So like 8, if you use V is equal to polynomials over a field, that's a vector space. You can also look at polynomials in 2 variables. That's a vector space. You can look at polynomials in n variables. That's a vector space. And in my notes, I have about 2 pages where I give you notation to work with those examples. Like a nice notation is just to use the sum to infinity and just assume that you've got finitely many non-zero things. That's a nice way to define a polynomial, right? Like, I guess I can write here, f of x, an element of this guy. We could say f of x is equal to the sum, let's say I equals 0 to infinity of c sub I x to the power I, such that what? Finitely, well, such that only finitely many c sub I not equal to 0. That's a nice way to work with polynomials if you don't want to fuss with like what's the degree that you're working with. If you just want to add polynomials, like it's pretty clear. Think about this. Why do polynomials form a vector space? Well, think about it. If you take 2 of these and you add them together, how do you add polynomials? You add coefficients, right? That's our definition. We add coefficients, like matching coefficients, like you learned in algebra, right? You group like terms and you add the coefficients of the like terms. Same definition here. And so if you do that, if you have 2 things that have finitely many non-zero coefficients, when you add them, you still have finitely many non-zero coefficients. So the sum of 2 polynomials is once more a polynomial, right? And anyway, So I could easily eat 20 minutes of class writing all my notation for polynomials on the board, and we would get very little out of that. Okay, so are there any other examples of vector spaces? What do you guys think? Sure there are, right? We could mix and match. We could do things like make a matrix of functions of matrices. And you can keep, you keep adding levels to this if you want. Like combine, make mixed examples, things like that. And you'll see some of that in the homework, just for the sake of, I guess, giggles. The other example that comes to mind that's very common in applications is like the solution set to a differential equation. But I think that really belongs more in the next section, perhaps. Trying to think of anything else. I think these are the main big examples. So do always read my notes. My notes always say something I forget to say in here. Oh, I know what's the problem. I was glancing at the page that I haven't gotten to yet. That's why that example was out of order, because it's out of order. Now the nth order polynomials, I guess I should mention this. We do sometimes work with polynomials like of lower order. So, rats. So another notation I should mention is Pn of f. This would be things of the form, an x to the n plus plus a1x plus a0, such that a0 through an are in the field. In other words, this is the set of up to nth order polynomials with coefficients from the field f. Here's how this works. We can talk about constant polynomials, and I'll keep it real for a second here. Those are a subset of the first order polynomials, whose graphs are lines, but those are not linear functions, by the way. And that is a subset of quadratic polynomials. Although, to be clear, those aren't all quadratic, right? Because 0 is in there. And the linear polynomials in there. So I should say possibly degenerate quadratic polynomials, because quadratic insists that the leading degree is 2, yeah? So sometimes I'll slip up and just call them quadratic. But anyway, this goes on. You got the nth order polynomials, and so forth. All of these are nested inside the set of all possible polynomials of arbitrary order. And this is the way of the world. These are all vector spaces, all right? But we're starting to see a concept here, which is a subset of a vector space, which is itself a vector space, right? This has a name, all right? And that's the subject of the next section here. So let me talk about that. So definition. Let V be vector space over a field F, period. If W is a subset of V, all right, such that W is a vector space over F, vector space over F, with respect to the operations of V restricted to W, then we say W is a subspace of V. And we write W less than or equal to V. I would like to point out to you, I don't know if you can tell it in my handwriting on the board or not, but there is a significant difference between this and that. Subset, subspace. Not the same thing. So you want to have a handwriting where I can tell the difference between those two, okay? Otherwise, I'll assume you're wrong. But I have enough points already. Actually, I have no points yet. I haven't taken any of your points yet, right? You have all your points. Let's keep it that way. So actually, it's easy enough to check that like any of the polynomials, they're subspaces of the vector spaces that are above them. Like P0 is a subspace of P1, P1 is a subspace of P2, P0 is also a subspace of P2. They're all subspaces of the set of all polynomials. All right? Actually, most of the interesting examples of vector spaces come from the subspace construction. All right? So more often than not, we're really interested in the context we already know, which is one of my basic examples we threw up on the board here today. Matrices, functions, combinations thereof. One of these contexts, one of these backdrops, if we take some subset of that, is it a vector space, all right? That's the interesting way to construct most examples. Many examples are from this. And the critical tool that you want to use for that is the so-called subspace test. All right? And here's the subspace test. If I can put it, I'll put it over there. By the way, the thing on the sideboard, what I'm saying there, guys, is you are allowed to assume that the finite sums commute. If you have a sum over I and a sum over j, you notice in some courses we use the notation like sum over I comma j. You've seen that, right? The reason that makes sense is that finite sums commute. This could be proved by a double induction, right? You could give arguments similar to the ones I gave last time to prove that. I have not put that on you. You're welcome. And so, but you can assume that it's true. You're going to need that for the associativity proof, also for the trace of AB is equal to the trace of BA proof. At least I needed it for both of those. Anyway, subspace test. Theorem. This is an important one. This you'll need for the homework. So subspace test theorem, just the end of the homework though. Or just subspace test. Let V be vector space over F and W a subset of V with W non-empty. Then W is a subspace of V if and only if the following conditions hold. Number one, if X and Y are in W, then X plus Y is in W. And number two, if X is in W and C is in your field, then C times X is in W. So we have, so the first, of course, is called closure under vector addition, all right? And the second one is closure under scalar multiplication. Now, let me just tell you guys a sneaky trick here to save yourself writing. Like, it kind of depends on the example, honestly. There's many examples where it's helpful to actually do this as two separate things. But you may remember from 221, when we were talking about linear transformations, it was also helpful to like group the additivity and the homogeneity into like one foul swoop. So if you think about this logically, you could replace these two with showing that cx plus y was an element of W, right? If you could do this for arbitrary x and y in W and arbitrary c in the field, you can simply take the case c equals 1 to get additivity and the case y equals 0 to get the scalar multiplication closure, right? The other thing to notice here is this, you got to pay attention to that because that's the thing students forget is they get tripped up on that. They forget to check that. More often than not, as a point of habit, I check that by making sure 0 is in the subset. Let's work an example here. So this one's a lot like one of your homework problems, so it should be helpful. This is example 1. Whoa, it's example 1. All right, example 1. Let's think about, let's see here. So we could think about V as, I'll keep it real, n by n matrices, right? That's a vector space. And we could look at W equal to A in our n by n such that A transpose is equal to A. If I'm accidentally working your homework problem, I'm sorry. I think it says anti-symmetric in your homework though, so I think I'm not working it. I'd like to show that that's a subspace. All right? So first order of business, is it a subset?
Yeah.
Yeah. So this is clearly a subset of, Rn by n by construction. And 0 transpose is equal to 0. Therefore, 0 is an element of W. Which means W is non-empty. So we've got that. So what do we do next? Let A and B be elements of W. Then A plus B transpose is equal to, if only someone had done a homework. Some of you will do homework problems this weekend when you get around to doing homework. I don't know, maybe you did it already, whatever. A transpose plus, maybe you guys just understand, that's why nobody's asking me questions. So that's a property of transpose, you're proving it in the homework, it's actually pretty easy. But that's equal to what? A plus B, since A and B are in W, right? So what's the condition to be in W? Has to be n by n matrix such that it's symmetric, right? It has to be equal to its transpose. So I'm using this condition here and here. And I can do that because they're in W. But then what have I shown? So you think of a subspace like a club, right? Like every club's got a condition for entry, a certain kind of dress. Like in order to come to Liberty, you have to meet a certain dress code, right? In principle, there's this dress code here. And in order to come here, you have to meet the dress code. So if you don't, then you're not in there, right? I mean, I know this analogy is really breaking down very, very quickly, but I'm told that these places called clubs that if you're not properly dressed, they won't let you in. So anyway, this is the condition to be in the club. So A plus B is in the club. It met the condition, right? So therefore, A plus B is in W. Next up, let C be in the reals and A be in W. Then CA transpose is equal to C times A transpose is equal to, well, let me write it up here. Then A transpose is equal to A, thus. Sometimes it's nicer to write this up here than have it down there. Thus this is equal to this, which tells me what? CA is in W. Therefore, by subspace test, W is a subspace of V. There you go. This is our first honest to goodness linear algebra proof. Did you understand it? See, it doesn't have to be bad. We just have to, now, okay, so it begs the question, how do you prove the subspace test theorem? So the proof of the subspace test theorem is very boring. It basically just is, if the operations of the subspace are the operations of the vector space restricted, then it's automatically true that they satisfy all those axioms. That's the proof. Literally the proof. Now, so think about this. What are other subspaces for examples I've given? You know? Can you guys think of any? How about function space? Let's think about real valued, let's think about S being R, and so like thinking about functions from R to R, functions on R, right? If we think about that context, think about, you know, V equals to the functions from R to R. Can you guys tell me, for this, subspaces? Can you tell me any subspace? Yeah.
Would polynomial space?
Yeah.
Subspace of function space?
Absolutely. We could take polynomial functions. That's a subspace of function space, for sure. Right? All of those, in all those subspaces of the polynomial space as well, right? What else? How about this? If you have two continuous functions and you add them together, do you get a continuous function? Is 0 continuous on R? Sure is. So apparently the set of continuous functions is a subspace of function space. How about differentiable functions? If I add two differentiable functions together, if I can differentiate one, I differentiate the other, can I differentiate the sum? Yeah. Well, yeah, you proved that in Calculus 1, the sum rule, right? What about twice differentiable functions? If I can calculate, you know, the derivative of a function and, wake up computer, the derivative of, come back to us. If I can calculate the derivative of a function and the second derivative, is the second derivative a linear operator? I mean, is the second derivative of f plus g, f prime, is f plus g prime prime equal to f prime prime plus g prime prime? Search your hearts, you know it to be true. This is also true for third derivatives, for fourth derivatives, for fifth derivatives, and so forth. So any of those, however many times differentiable function, set of how many times differentiable functions you'd like, those are subspaces of the set of functions. Smooth functions, functions which have arbitrarily many derivatives, that's a subspace of function space. We could go all day, right? There are all kinds of qualifiers that you can make for function space that give you subspaces. Now this is where the differential equations example comes through. So differential equations is, if you have, you know, like a second order differential equation, for example, these are the solution set we'll learn in differential equations eventually, that the solution set actually is like C1y1 plus C2y2, right? And so one of the things we'll learn is that the sum of solutions to a linear homogeneous differential equation is again a solution to a linear homogeneous differential equation. That means that the solution set to a differential equation will satisfy the subspace test. And so like the solution set to a differential equation is again a subspace. So subspaces are like everywhere. Now what I wanted to show you guys here is something, I don't think I gave you guys any homework like this. I just wanted to like reason through it with you because it's picky. Well, this will get me on a bad day. Like I will get, well, I'm way, that's the future. Let's see here. Let's try 35 maybe. Hey, come on. 33? Why won't it? Oh, numlock. Well, that's, all right. I will get to it eventually. Okay, so those are all the examples we looked at. Here's the notation that I was mentioning. You know, like I've got, oh, I'm sorry, it's too tiny. So some of the stuff isn't especially like, you could do 2 by 2 matrices of quadratic polynomials. Like each one of these would be a quadratic polynomial in X. That's a kind of vector space. And the most important example I didn't cover today, and I'll get back to this another day, is like the Cartesian product of two vector spaces. We'll talk about that another day. I shouldn't hurry through that. This is important. So past the axioms of a vector space, there are certain logical consequences that we want to know and we want to use. And I don't want to make you guys prove these, like reinvent the wheel. So if we're in the context of a vector space, you have these things to use, all right? So in particular, 0 times x is 0, c times the 0 vector is 0, minus 1 in the field times x is the additive inverse in the vector space. And if we have a scalar multiple times x being 0, missing a dot right here. That bothering you, Violet? No? Okay. Missing a dot right there. If you have a scalar multiple times a vector being 0, either the scalar is 0 or the vector is 0. We can prove. And a lot of these follow first from the law of cancellation. And let's work through that. So you have, x, a, and y vectors in a vector space. Suppose xa is equal to ya. Then x is equal to y. You're like, okay. Yes, but let's prove it from the axioms. So suppose that x plus a is equal to y plus a. By axiom 4, we know that there exists an additive inverse to a minus a. So we can add that to both sides. All right? And so we add it to both sides. Then by axiom 2, which is associativity of addition, we can regroup. So we have addition of a and minus a. But by definition, that's 0. So then we have x plus 0 equals y plus 0, which then gives us x and y, so x equals to y. That's the law of cancellation.
Is that a typo that says x plus 0 equals 0?
Oh yeah, it's supposed to be x. That is most certainly a typo. Thank you. Muchas gracias. I should fix that. I guess it just goes to show you no one reads the notes. You're like, it could also show that the professor never makes corrections that he's told about. That's another possibility. We'll never really know which one it is. And like, here's the proof of 2. So why is this parentheses missing here, I think? Maybe not. So I've got c times 0 plus 0 is equal to c times 0. Well, that's true, right? Because anything plus 0 is the vector again. And then what I did is I took 0 and I wrote 0 as 0 times 0, which is also allowed because that's how 0 works. But then I used the distributive property, and I got c plus 0, c times 0 plus c times 0. So I've got this is equal to that. Then by the cancellation thing, which we already proved, it follows that that has to be equal to 0. And that's how you prove that any constant times a 0 vector necessarily by the axioms of a vector space have to be 0. And you might say, well, okay, but isn't that already obvious for examples? Well, yes. But the larger point here is that the larger point of the mathematics we're doing is we're trying to distill a large class of examples into its fundamental whole. The fundamental whole is captured by this axiom system. And so anything we can prove from the axioms is not true for just one example, it's true for every single possible example that we come up that satisfies the axioms. So that's very useful. It's also useful as a check that an example is not a vector space, right? If your alleged vector space violates one of these identities, it's not a vector space, right? So what I haven't showed you today, and I really should show you some of these at some point, is like, what are some examples of things that are not vector spaces? Can you guys think of any of those? We've got like a minute. I think I have some in here. Yeah.
The null set.
The empty set is not a vector space. That's right, because it's what?
It's nothing.
Yeah, it's got nothing in it. Nothing. But the set just containing 0 is a subspace, so it's a vector space. So that's different than the empty set. Some of you talk about nothing and the empty set as if they're equivalent. This is something you need to get out of your system because it is unhelpful. In this class especially, any line through the origins of subspace, any plane through the origins of subspace. On the other hand, if generically speaking, if your characterization of something involves inequalities, it's not going to be a vector space. Like, for example, if you take just like the positive quadrant, x, y, subject to the regular vector addition, this is not a subspace because if you take any negative number, Scalar multiplies it out of there. Also, 0 is not in there. That's usually a dead giveaway. A lot of examples are not subspaces because they don't have 0. So this makes a good kind of test question. Here's a set. Is it a vector space with respect to the usual vector space addition? This is a very decent test question because basically it's a way I can test the axioms, because you can use any one of these axioms failing to strike down it being a vector space. That's the main use of the definition directly. More often than not, we'll be using subspace test theorem to set up the existence of it being a vector space. So the problems you have in your homework are mostly about that from the book, I think. There is one, the first one I asked you guys from the book. That one might be hard. So I don't know. Anyway, I think that's it. Have a good weekend, you guys. If you want to stick around and ask me Physics 2 questions, you're welcome.